This is a quick review of chemical bonding. We will look at modern atomic theory, electronic structure, and covalent bonding, Lewis structures, and then we'll look at 3D structures, which we do need moving forward in organic chemistry. We have reviewed this work before in general chemistry, and here again, we'll repeat the process. Summary of the modern atomic theory is really atomic structure consists of subatomic particles. The nucleus itself consists of protons and neutrons. They're quite heavy compared to the electron, which has significantly less mass. The proton itself within the nucleus is positively charged. The electron is negatively charged, but most of the atom consists of free space. We need to know exactly the movement of electrons. But according to Heisenberg's uncertainty principle, it is not possible to determine both the position and the momentum of an electron. And so Schrödinger came along and had a chat about the wave function. And he gave a description of the energy of an electron within the field of the nucleus. With are these atomic orbitals. These are wave functions, and they have amplitudes, i.e. the size and numerical magnitudes of these guys. There's signs, which can be positive or negative, or we can call them flavors, and nodes. These are the values of the wave function, and it usually gives you some sort of 3D idea of your wave function. We call these atomic orbitals. Now is look at individual atoms via the electronic structure and then see if we can use these models to combine them and form covalent bonding. We have to start with the periodic table, and in the periodic table we have these groups that are the columns from the lightest to the heaviest in that column. These are groups. And then across, we have periods. So hydrogen and helium is period 1. From lithium through to neon is period 2, and so on. Altogether, then, we end up with the electronic configuration that are present in the periodic table. And I've only shown a few of the elements that we are concerned with in organic chemistry. We don't want to expand too much at this early stage. And you can see that, for example, if you look at carbon, we see that carbon has a 1s2, 2s2, 2p2 electronic configuration. The 1 in this case is the principal quantum number, while S is, of course, the magnetic moment, and 2 the number of electrons in that particular orbital. These electronic structures or electronic configuration using these ideas. The Pauli exclusion principle, which stated that no two electrons can have identical quantum numbers. So a maximum, you can only have 2 electrons present in an orbital. The Aufbau principle, which is the filling up principle, is that in the ground state of the species, in this case we're looking at the atom, electrons fill from the lowest wave function or the lowest orbital upwards. Degenerate orbitals, this is just some nomenclature, degenerate orbitals are orbitals that have the same energy. So for an atom in the ground state, the 2px, 2py, and 2pz, these are all degenerate. And finally, we have Hund's rule, which states that the electronic configuration with the highest multiplicity, i.e. the number of unpaired spins, is more stable. We can see this at work. So if you notice carbon, which has atomic number 6, we can use the Aufbau principle with Hund's rule and start filling up this species. You can see that we have 6, so 2, 4, 6, and we notice that we have 2 unpaired electrons in the p orbs. If you look at oxygen with atomic number 8, same sort of thing. But in this case here, you can see that we have 4 electrons in the 3 2p orbitals, and we still have 2 unpaired electrons. This, of course, filling out principle is the off-bar principle, and herein you can see where we have only 2 electrons of opposite spin in the 1s, etc. This is Pauli's exclusion principle. Herein, where we have the 2 unpaired electrons in the 2 degenerate orbitals, this is Hans' rule. The significance of the electronic configuration as it relates to chemical bonds is this. Electrons in the highest principal energy level are called valence electrons. These are the electrons that are involved in bonding. And we normally use Lewis dot representations of atoms, and these dots are really valence electrons, i.e. outer shell electrons. And we relate these because these will combine together to give us chemical bonds. To have examples of the electronic configuration and valence electrons, we have here boron and phosphorus. Note that the electronic structure of boron is 1s2, 2s2, 2p1. With a configuration like that, to illustrate it, you'll note that there are 3 electrons in the highest principal energy level, meaning that the Lewis dot structure could be represented like this. So we just got the element, the name of the element, and we surround it with 3 electrons. With phosphorus, belonging to group 15, we have 3s2, 3p3 as the valence electrons. If you notice in this illustration, here they are, 3 being the highest principal energy level. And so to represent those 5 electrons, we have the phosphorus symbol surrounded by those 5 electrons. We say that phosphorus, being in group 15, has 5 valence electrons. Be even more detailed, because if we look at the valence electrons, for example, of beryllium, we could see that the core 1s2 is involved with that formula itself, and then those 2 electrons are the valence electrons. So the 1s2 is the core. We say that beryllium has an helium core because the configuration of helium, if you remember, with atomic number 2, helium has a configuration of 1s2, and so the core of beryllium, being the 1s2, is a helium core. At our Lewis dot symbol now for these periodic tables, and you will see that immediately, if you move here to the arsenic, which is in the same group as nitrogen, then this also has 5 valence electrons. If you look at fluorine, has 7 valence electrons, so we say that this has a valence of 7, and the same thing with bromine and iodine. All these fellas in group 7 have 7 valence electrons. The essence of this is quite simple. We can use these ideas now to decide on what type of bonding our atom is going to be involved in. So for example, here we know from past chemistries that the alkali metals, which include sodium, they form bonds by donating electrons. In this case here, it will donate to a chlorine. Chlorine, on the other hand, will accept electrons. So sodium now has a positive charge. The chlorine now has a negative charge. So we have the sodium ion and the chloride anion, and they attract each other electrostatically, and they are stacked in a type of lattice structure. This is an ionic compound. There are a number of bonds that we can think of. Ionic bond, but the covalent bond. And the covalent bond is involved with the sharing of electrons. Let's look at an example. We are going to look at the molecule chlorine. And, well, the chlorine molecule is Cl2. So how does this relate? Well, the valence electron of chlorine is 7. And we're going to have two chlorines combining together to give us a shared pair. So remind yourself that each chlorine needs to gain an electron to get that octet. This is the octet in this case will be the neon octet because we already have a certain core. Now, look carefully. We have this chlorine and we combine with that chlorine, and now they're sharing electrons. They're sharing a pair. This chlorine is satisfied because it has 8 electrons around it. This chlorine is also satisfied because it's 8 electrons around it. So they both share electrons and both are happy with this octet. This shared pair is called a bond, a covalent bond. This is a single covalent bond. And now we have a chlorine molecule called Cl2. Transfer this idea to oxygen. You will notice that the oxygen has 6 valence electrons around it, and therefore, when combined with another oxygen atom, we will have a double bond. The double bond is indicated by having the 2 oxygen atoms with 2 lines in it. It's telling you got 2 shared pairs, and of course the the molecule itself is O2. So let's talk about electronegativity. Electronegativity is a measure of the tendency of an atom to attract the bonding pair of electrons. Note that fluorine has got really high electronegativity compared to hydrogen. And so when you form covalent bonds between hydrogen and fluorine, then there's a huge difference in electronegativity. We end up with what's called polar covalent bonds. So, for example, if you look at carbon-carbon bond, the electronegativity difference is 0. And so it's on this left-hand side of the scale, while with carbon-oxygen, the electronegative difference is quite decent, and so it's quite inside the scale. And so we have what's called a polar covalent bond compared to the pure covalent bond of the carbon-carbon. When it gets to the extreme, such as the lithium-carbon bond, you now have an ionic bond, or almost an ionic bond. When you get to sodium chloride, then it's a purely ionic bond. So we can state safely that the polarity of a bond is determined by the difference in electronegativity. And we can state that nonpolar bond is because the electrons are shared equally. Now, if the atoms have greatly differing electronegativity, then of course the species is very polar, equal to an ionic species. We can further indicate the nature of the covalent bond by using electrostatic maps. Note, for example, that we have here a species that tells us that the more positive end of the bond will have a blue color, meanwhile the negative end will have a red color. So when we look at fluorine, we know it's neutral, i.e. the electronegative difference is 0, i.e. we have a pure covalent bond, compared to hydrogen fluoride, which is rather polar. So we can go ahead, and once we generate that map, you can see that the chlorine itself is quite red in this region, meaning that it's quite electronegative in that region. And in this region here, you can see that we have the fluorine, which is quite, the hydrogen, which is quite blue. We can also indicate the direction of the polarity by using this arrow, note straight arrow with this cross at the end, at the tail, to tell us that the positive end is at the hydrogen and negative end here is at the fluorine. Now let's delve into bonding, and the first species we'll look at are Lewis structures. And there's some simple rules for drawing Lewis structures. Firstly, we got to figure out the number of valence electrons in the whole molecule, and then we draw skeletal arrangements of those atoms. The atoms that are usually bonded to carbon include the nitrogen, oxygen, or hydrogen, with some exceptions, of course. The general bonding in the neutral species is tetravalent for carbon, trivalent for nitrogen, divalent for oxygen, and monovalent for the halides. This is group 7. We have to distribute electrons, but pairs of electrons, so that we follow the octet rule, except for hydrogen, which follows the duet rule. If there's not enough electrons around, then of course we use bonded pairs. We go for double bonds, and then we compute formal charges and evaluate the structure. So for example, we have this. It's a phosgene. Its formula is COCl2. We're going to assume that carbon is a central species. And if carbon is a central species, then of course we're going to draw this structure here. Now note, the total number of electrons in the compound is 24. Yeah, because we got one carbon with 4 valence electrons, one oxygen with 6 electrons, and 2 chlorines belong to group 7, so that's 14 electrons. So the total number of valence electrons is 24. When we build our skeleton using carbon as a central atom, we have only 6 electrons. That's 3 pairs. That means we need another 9 pairs, because that's a total of 12 pairs, 24. So we go ahead and we start to build. And note quickly that we start to add pairs of electrons around each atom until the octet is satisfied. Note, the octet is satisfied for both the chlorine, the oxygen, and yet the carbon itself is deficient because we need to obey the octet rule. And so what we do is we form a double bond between the carbon and the oxygen. So one of the shared pairs, one of the lone pairs became a shared pair that was an oxygen. And now we've satisfied that structure. We could not have shared anything with the carbon, with the chlorine, because chlorine, being that it is a halogen, is satisfied being monovalent in its neutral state. Let's look at another species. Ethene is C2H4, and the total number of valence electrons is 12. And when we build the skeleton, we have 2 central carbon atoms flanked by hydrogen. So it's quite a symmetrical molecule. But at the present moment, we only have 1, 2, 3, 4, 5 pairs of electrons. They are shared pairs at the present moment. Yet we need another pair, because 12 electrons equal to 6 pairs. And so those 2 extra pairs that of the pair that we need, we can add it onto a carbon, because the duet of hydrogen is already satisfied. However, you can see that the carbon on the right, totally ambiguous of course, is unsatisfied. The octet is not present. And so to satisfy that, we take this lone pair and make it a shared pair here. And so we end up with this. This is the Lewis structure for ethene. And you can see that in ethene, there is a double bond between the two carbons, what we call a carbon-carbon double bond. To compute formal charges, we need to look at the formal charge, which is the valence electrons minus the number of bonded electrons and the number of unshared electrons. In a neutral molecule, the sum of the formal charge is always 0. For an ion, the sum of the formal charge is equal to the charge of the ion. And the atom in the Lewis structure that has the number of bonds expected on the basis of its group number has no formal charge. Let's look at this in detail. Can follow. So if you look closely at this example, we can see that what we need is the formula which states that the formal charge equals to the number of valence electrons minus the number of bonds plus the number of unshared electrons. So we can say that carbon, the number of valence electrons in carbon is 4 minus the number of bonds, in case of A, which is 4, minus the number of unshared electrons, which are 0. So if you look closely, the answer is 4 minus 4 equals to 0. So we immediately know that the formal charge of A, carbon A, is 0. So that means we can extinguish D and E. We move on to B. The formal charge of B, again, the number of valence electrons on the carbon is 4 minus the number of bonds. In this case, we have 3 plus, should state, plus the number of unshared electrons, which again, I do not see any shared electrons, 0. So 4 minus 3 equals to plus 1. So your answer there should be B. Does that make sense? Covalent bonding patterns that you should familiarize yourself with. But herein, you can see that all these species are neutral. So carbon is always tetravalent when it's neutral. So even though we have here a carbon with these two double bonds surrounding it, but it is 1, 2, 3, 4 shared pairs. If you note, nitrogen is in its neutral form is always trivalent with a lone pair. Trivalent, 1, 2, 3 bonds. That's trivalent, and there's a lone pair. So whatever flavor of nitrogen you have, if it's trivalent with a lone pair, it's neutral. Formal charge equals to 0. Oxygen. Again, you can see oxygen. Yeah, double bonded oxygen is neutral. And in this case here, you can see it is divalent. How I usually think of it is this. If I think of the hydrogen compounds of these, so for example, methane, CH4, ammonia, NH3, water, H2O, and of course, a hydrogen halide of some sort. Say, for example, let's think of hydrogen chloride. So we got 1, 2, 3 unshared pairs of electrons around the chloride. This differs from species because, note, carbon, when it's trivalent, can be negative or positive. Nitrogen, on the other hand, if it is positive, it is always tetravalent. But when it is negative, formal charge of -1, it is divalent. Oxygen is trivalent when it's positive. And how I remember these is nitrogen, for example, tetravalent nitrogen, I can remember from my general chemistry, NH4+, the ammonium ion, while, for example, we can start thinking of this guy here. This is the amide. The oxygen we can think of here, we can think of hydronium. So that hydronium, of course, remember? And herein, we can think of the O- as that what we saw in the hydroxide. Does that make sense? So herein, we can look at diazomethane. And note, with diazomethane, the total number of electrons in the molecule, or valence electrons, I should state, is 16. And remember our rules. We draw the skeleton, add electrons, followed by obeying the octet rule. And we'll notice that we have two reasonable Lewis structures. The fact that we have two reasonable structures tells us that we have an idea that's called resonance. Note the difference in the formal charges. Resonance. So two viable Lewis structures from the same molecule. We will expand upon that. By this particular problem set. Again, remember our formula. The formal charge is the number of valence electrons minus the number of bonds plus the number of unshared electrons. So herein, we have the carbon with 0. The nitrogen, you should have calculated this nitrogen A would be 0. The nitrogen here at B would be +1. And that of C will be -1. So A, 0, that does not give us much options. B, being +1, we can get rid of E and A. And then, of course, N being -1 leaves us with just C. We'll cover the three-dimensional structures of molecules because Lewis structures are not a true depiction of the molecule. To be more accurate, we need bond angles as a way to illustrate the geometry better. Herein we can predict ideas like molecular polarity, stereoisomers, etc. The VSEPR model for molecular structure. This is the valence shell electron pair repulsion model. First, we're going to draw the Lewis structure. We're going to count the attached atoms and lone pairs of electrons and then determine the arrangement that will minimize said repulsions between those pairs. We're going to then determine the position of the atoms and the lone pairs and predict the structure. So, for example, if we look at methane, methane has 4 shared pairs of electrons around it. So these pairs of electrons repelling each other literally forms a shape that is a tetrahedral. So each one of these hydrogens are pointing towards the corner of a tetrahedron. You will say the same thing with ammonia. Ammonia has 3 NH bonds and a lone pair. All 4 pairs of electrons, again, point towards tetrahedral space to minimize the repulsion between them. With water, again, we see the same thing, because the water, note, has got 4 pairs of electrons, 2 shared pairs and 2 lone pairs. Again, they point into tetrahedral space. When I look at the bond angles of this tetrahedral species in methane, it's exactly 109.5 degrees. This is the bond angle of a pure tetrahedral species. On the other hand, if you look at water, of ammonia, you will notice that the bond angle is slightly less between those NHs. Why? Because the lone pair on the nitrogen is more repulsive than the shared pair. If you look at the water, there's even a greater degree of compression. So now we have a bond angle of 105.5 degrees, 104.5 degrees. Now, notice that this is the electronic environment of the molecules that we have here, i.e. tetrahedral. So we have methane, ammonia, and water are in a tetrahedral electronic environment. However, if we look at the molecular geometry, then something interesting happens. We look closely at the methane, we realize that all 4 species, 4 hydrogen, are pointing towards the corner of a tetrahedral, meaning that we have a species that's in tetrahedral space. Now, if we look at ammonia, we have 3 hydrogens at the base of a pyramid where nitrogen is at the apex. With water, we only have this molecule that is bent. There's only 2 hydrogens bent. Now, all of these species, of course, we know that they are in a tetrahedral electronic environment. So therefore, the water is bent. The ammonia is a trigonal pyramidal species, and the methane is tetrahedral. These are the geometric shapes of these molecules. So again, let's look at, say, for example, carbon tetrachloride. Carbon tetrachloride, the Lewis structure, is a species with 4 carbon chloride bonds surrounding the carbon, meaning that with repulsion minimized, we have chlorines pointing towards the corner of a tetrahedral. So the electronic environment is tetrahedral. And if we look at this ball and stick structure, you can see the chlorines are pointing to that corner of, pointing towards the corner of the tetrahedron. So this is a pure tetrahedron, bond angle 109.5. In contrast, phosgene, note, we got a carbon double bond O, a carbon chlorine, and a carbon chlorine in the Lewis structure. But we got 3 blocks of electrons. 3 blocks of electrons. And so when they repel each other, then they point towards a trigonal planar species. So the electronics is trigonal planar. And of course, the resulting shape, geometric shape, is a trigonal planar system. Now, note, the bond angle would be approximately 120 degrees. Now, can you think, would this carbon-chlorine bond angle be less or greater than 120 degrees? Nitrile is also another interesting species because, as you can see, we have here a Lewis structure for the carbon. This carbon, of course, is tetrahedral, but this carbon is linear. And so therefore, when we have the ball and stick, you can see that it leads to quite an interesting geometry, because the carbon, which is sp3, is quite different from the carbon which is triply bonded to the nitrogen. This has linear geometry. Discuss molecular polarity. And first thing we got to realize about molecular polarity is molecular polarity can lead to a number of interesting properties, such as boiling point, melting point. It can decide on the type of reaction you have, solubility, etc. And one of the things that we do with molecules, once we find, say, for example, a net polarity that this compound has, chloromethane, is that we can draw an electrostatic potential map, similar to what we looked at when we looked at polar bonds. And you can see that the overall molecule has a polarity pointing towards the chlorine. Again, remind yourself of the color scale. The blue is, of course, most positive, and the red is most negative. Molecule is a molecule that is electrically asymmetrical. So it causes it to be oppositely charged at 2 points. And you can see with the hydrogen chloride, we have an interesting polarity pointing towards the chlorine. And the water has a polarity, a dipole pointing towards the oxygen, and acetone has a dipole pointing towards that oxygen. So all these molecules here have a molecular dipole because of the asymmetry that's present in them. Dipole. We got to realize that for molecules with multiple polar bonds, the dipole moment is the vector sum of all the individual bond dipoles. Note that with symmetrical molecules, such as carbon dioxide, there is no dipole moment, because even though the carbon double bond O is quite polar, there is another carbon double bond O in the opposite direction. So these two vectors are equal and in the opposite direction, so net zero. Carbon tet, the same thing. All 4 carbon chlorines are pointing towards tetrahedral space equally. And so again, a net dipole of 0, the bi. However, asymmetrical molecules have dipole moments reflecting the contributions of individual dipoles. So herein, for example, if you look at chloromethane, we have a dipole moment of 1.87 dBi. Now, realize this, that molecular dipoles are greater than individual dipoles. For example, in that said chloromethane, the carbon chlorine that is present is 1.5. However, overall, the molecule is 1.87. We'll now focus our attention on valence bond theory or hybridization theory. This is a mixing of atomic orbitals in order to achieve what are called hybrid orbitals. Now realize this, we'll be using VSEPR geometries to predict hybrid orbitals. We start off with our Lewis structure and then generate our VCRP model. And note that the tetrahedral atom is what we call an sp3 hybridized atom. Now, the tetrahedral center, of course, is carbon. So carbon is sp3 hybridized. How did it achieve this? It achieved this by mixing the 4 valent atomic orbitals of carbon and included the 4 valence electrons of carbon. This by mixing the carbon 2s orbital and 3 carbon 2p orbital to give us 4 hybrid orbitals, because if we had stayed with the unhybridized carbon, we would only have a valence of 2. But with the hybridization or mixing, we now have 4 sp3 hybrids pointing towards tetrahedral geometry space, and this is a place where we can put our 4 electrons from carbon. So now we have an electron each in each sp3 hybrid orbital. These hybrid orbitals will now overlap with the hydrogen 1s. Now remind yourself that each hydrogen 1s has an electron present. So if you think about the overlap that occurs, then now we can have those 1s electrons in those hybrids as well to realize our octet. So each carbon has an electron in each of its hybrids, and then of course there's a hydrogen with an electron in its 1s. Realizing then our octet. Model is ethene, and ethene is interesting because ethene, from our VSEPR, we saw that ethene is a planar structure. Each carbon is doubly bonded. Now, exactly what does the hybridized model looks like? It's quite simple, because each ethene is sp2 hybridized, and there is overlap with each carbon in an axis. This is the sigma overlap, and there's also overlap of sp2 hybrids with hydrogen, also sigma overlaps. The remaining p orbitals overlap in a plane, and this is called a pi overlap. We've seen this before. The pi overlap, hence we now have a double bond. Linear molecule acetylene, or ethine, you can see is a triply bonded species. And if we went through the same model that we did with the methane, you can see that we now have sp hybridization. We've mixed one s and one p, and there are 2 p orbitals that are not involved in hybridization. Hence, there is sp overlap between carbons, sp overlap between carbon and hydrogen. The remaining 2 p orbitals undergo pi overlap with each other, and therefore we realize the triple bond. Valence bond theory affects our bond length, the strength, and angles. Well, it's quite obvious that if we're sp3 hybridized, then our bond angle will be tetrahedral, so of course 109.5, compared to, say, an sp hybrid species, which is a 180. But more interestingly is when we move to bond length. Now realize this, the more S character you have in a molecule, then the more efficient the overlap is. So in this case, the 2 carbons are sp3 hybridized, and so therefore the sp-sp hybrid overlap realizes an efficient 1.2 Armstrong in length. It's much shorter compared to the sp3 hybrid overlap that's present in the carbon-carbon of ethane. This is also reflected in the sp hybrid overlapping with the hydrogen 1s in ethine. Again, you can see 1.06 Armstrong compared to the sp3 hydrogen 1s overlap, which is 1.10 in ethane. With bond strength, we see another characteristics. The more efficient the overlap, or the more shorter the bond, then of course, the stronger the bond. And in this case, you can see that here we have bond strength 967 kilojoules per mole for the sp-sp overlap compared to 377 for the sp3-sp3 overlap that we find in ethane. As I stated before, this is quite obvious. The shorter bond lengths, stronger bond strength. Smaller distances between nuclei, shorter, stronger bonds. And so sp3-sp3 overlap is not as efficient as the sp3s overlap. More S characteristics, the shorter the bond. So the triple bond, which has 50% S, is much shorter than that of the sp3 overlap. Looking at molecular orbital theory. Now, with Lewis and Valence bond theory, these were localized species, and we assume that all electrons are restricted to specific bonds between atoms or in lone pairs. In contrast, the delocalized approach to bonding places the electrons in molecular orbitals. So we're looking at the whole molecule. Achieved is by a construction called the linear combination of atomic orbitals. We state molecular orbitals are generated by atomic orbitals combining to create them. Electrons in these molecular orbitals belong to the molecule as a whole. And now this is in contrast to valence bond theory, which suggested that the electrons are shared by simple overlap of atomic orbitals or hybridized atomic orbitals. Simple approach. We have two-wave functions. In this case, we have the two 1s atomic orbitals, and they combine together. And they combine together constructively. And when they combine together constructively, we do get a lowering of energy. So the bonding probability density is lower in energy than the initial orbitals that we start to work with, or the initial wave functions that we start to work with. In contrast, we could have opposite signed atomic orbitals combining together, or different flavors combining together. And you can see that this is destructive. Overall, quite destructive. And what it means is that we have an increase in energy of the system. What we can do now is generate a diagram such as this, because what this diagram is a molecular orbital diagram generated from the two atomic orbitals combining together to give you can see a lowering of energies. So this is your bonding orbital. And then, of course, they combine together as well, opposite sides, to give an increase in energy. This is the anti-bonding orbitals. Now, we're talking about the hydrogen molecular orbitals. So therefore, we have two hydrogen 1s's combining together to give us the two molecular orbitals, sigma 1s, meaning that it is sigma overlap and is generated from the 1s orbitals, and sigma star 1s, meaning that it is an anti-bonding orbital that's generated from the overlap of the 1s. Herein we got some basic ideas. You can see that the number of molecular orbitals that we generated was from the number of atomic orbitals were combined. So in this case, we have two atomic orbitals combining together to give us two molecular orbitals. Realize that, we have a lowering, i.e. constructive overlap, and an increase in in energy, i.e. destructive overlap. Now, with the hydrogen atom molecule, for example, we fill in according to the off-bar process, meaning we start with the lowest energy level. There is a 2-electron system. Yeah, because each hydrogen brings 1 electron to the system. Yeah, that's located in its 1s orbital. And then those 2 electrons will sit in this sigma 1s, i.e. the bonding molecular orbital, and according to Pauli exclusion principle, they have to be of opposite spin. Remind yourself that degenerate orbitals fill singly before they pair up. This is Hund's rule, and we'll see this later. We move on. Let's look at this diagram, which shows the formation of a bond. Now, realize this, with the 2 atomic orbitals, this is the energy level that they have. Now, when they combine together constructively, you can see that as they approach each other, these 1s's, yet there is a decrease in energy, and here it's at an optimum at 0.74 Armstrong. Now, realize this, the 0.74 Armstrong bond mass corresponds to 105 kilocalories per mole bond dissociation energy. This is the energy of the bond. This is the bond of dihydrogen. Now, of course, once we start pushing the 1s's more together, then of course you can see there is an increase in energy, and until you get to infinitum. So what you want is an optimum, and this is where it is at 0.74 Armstrong. Make sense? We're looking at, say, for example, the 2 1s's combining together the bonding and the anti-bonding. With dihydrogen, you and I know that there's 2 electron systems that combine together to give you these 2 electrons in the sigma 1s, i.e. you get a bond order of 1. But what happens when we have, things like a 1 electron system like H2 plus, or a 4 electron system like He2 plus, 3 electron system, or 4 electron system like He2? Let's have a look. For the dihydrogen, which we already covered, we got this idea where the bond order, which is the number of electrons minus the number of anti-bonding electrons divided by 2, in this case, equals to 1. So the bond order is 1. It's really defining the HH bond. It's a single bond. But if you look, say, for example, at the H2 plus, you can see it's a 1 electron system, and herein the electrons in the bond is, in the bonding orbitals, is 1 minus the anti-bonding 0 divided by 2, and you have a bond order of a half. The same treatise with the He2 plus, which is a 3 electron system. So this is dihelium plus. And you can see that with this we have a bond order which is 2 minus 1 divided by 2 equals to plus a half. Now, look at this puppy. This is, of course, the He2. Now, if you look at the He2, then of course it's a 4 electron system, and note that the bond order is 2 minus 2 divided by 2 equals to 0. The bond order is 0. What does this mean? Well, obviously it means that there is no bonding between 2 helium atoms to form a helium molecule. So the helium molecule does not exist. Or if it does, it'd be very difficult. The lifetime would be very, very poor. Let's ask ourselves this question. Anti-bonding molecular orbitals are produced by, and of course, you can see that the answer will be a destructive interaction of atomic orbitals. We can move on to other systems, such as this is lithium and beryllium systems. Now, remind yourself, now these are in period 2, and of course now we have the 2s available to us. In the case of the lithium, you can see that we have a bond order 2 and 2, 4 minus 2 equals to 2 divided by 1. So the lithium, you can see it has a bond order of 1, but remember that these things are in some sort of metallic system. But lithium 2, it's telling you that it can exist. And the same thing here, you can see that beryllium-2, on the other hand, would have a bond order of 0. And so that does not look like it should exist. Continuing the theme of the two elements in period 2 combining together, you can see that first case here, totally arbitrary, we have the PZs overlapping across an axis to give us a bonding sigma 2p and then anti-bonding sigma star 2p. On the other hand, you can see that the remaining set of 2p orbitals will combine across a plane and to give you this planar overlap, which we call pi overlap. And herein we have the pi bonding and the pi anti-bonding orbitals. Now realize this, both these two sets of atomic orbitals are degenerate. So this pi 2p generated from the py's is equal in energy to this pi 2p generated from the px. The only thing is the plane is different. So we can now produce ourselves a molecular orbital picture that looks like this, because this is, of course, to deal with elements in period 2. Because as you can see, first of all, we have the two S's overlapping to give you a bonding and anti-bonding. We have one of the two P's overlapping with another of the two P's to give you a very stable sigma bonding orbital. Remind yourself that sigma bonds are more stable than pi bond. We then have the other two p orbitals overlapping. Remember, these are in different planes, but they are degenerate. Now, realize this. If we overlap the sigma and we generate this bonding orbital, then of course there has to be an anti-bonding orbital that's generated of equal energy in the opposite direction. And the same thing occurs with the anti-bonding of the pi. Now realize this, let's look at this again, because the pi is higher in energy, the pi bonding is higher in energy than the sigma bonding, but the pi anti-bonding is lower in energy than the sigma anti-bonding. Think about that for a sec. The first species that we're going to look at is the dinitrogen. Now remind yourself that dinitrogen, being group 5, has two sets of 5 electrons, i.e. 10 valence electrons. Why? Because remember now that the 1s2 is already buried, so we're not dealing with that right now. And if we take those 10 electrons in there and add them, you can see that literally, we got 1 pair, 2 pairs, 3 pairs, 4 pairs, 5. When you do the calculations, you can see that the number of bonding is 8, minus the anti-bonding, which is 2, and you divide that by 2, you end up with a bond order of 3. This is, of course, a triple bonded species. Now, let's look at dioxygen. Remind yourself that dioxygen has 12 valence electrons. It's in group 6. We've already buried the set of core electrons in the 1s sigma and sigma star. Now, if you look closely, those 12 electrons will fit in according to Aufbau. And so that's 6 pairs. So we got 1, 2, 3, 4, 5, 6 pairs. But look at the 6th pair, because the 6th pair is sitting in the pi star 2p. But not only that, they are unpaired electrons. We're putting them in these two degenerate orbitals according to Hund's rule, i.e. they have parallel spin. If you look at the bond order of dioxygen is 8 bonding minus 4 anti-bonding divided by 2. So that gives us a bond order of 2, which explains the oxygen double bond 2. But the coup de grace for molecular orbital treatise came about with this idea, because the normal Lewis structure of dioxygen does not show paramagnetism. Yet when we do the experiment, we see that paramagnetism exists, i.e. a compound with unpaired electrons. And herein is definite proof of the paramagnetism of dioxygen. And not ignore the fact that carbon and other atoms present in these molecules can exist as cations, they can exist as radicals, and they can exist as anions. We will look at carbon, and we'll look at the simplest species of carbon, i.e. that of the methyl cation. Methyl cation, of course, is trivalent. And if we think about the methyl cation that is sp2 hybridized, then of course the structure would be the sp2 hybridization species overlapping with the sp2 hybrids overlapping with the 1s with an empty p orbital. Now, if you look at the electrostatic, you see that it's purely blue, meaning that there's a strong presence of a positive charge. Look at the methyl anion. The naked methyl anion, you can see that it's trivalent. And of course, in this case, it is sp3 hybridized. And you can see that it is quite red because of the fact that it is an electronegative species, i.e. electron rich. What about the radical species? The radical species, of course, we can think of a species, and it has the sp2 hybridized carbon, and then we have a p orbital, but this time around, the p orbital that's perpendicular to the plane of the molecule has one electron present. You can see that we have this green electrostatic species, meaning that it is quite neutral. Well, next step will be to look at chemical bonding in its simpler format, i.e. line drawings. And we'll make sure that you press a like and ensure that you subscribe.